Picture this. It's 1929 and you're standing in the Topkapi Palace in Istanbul. The air smells of old leather and dust, that particular scent of archives where forgotten things wait in the darkness. Around you, wooden shelves stretch toward vaulted ceilings, each one packed with rolled documents, some untouched for centuries. You're part of a team cataloguing the palace's collection, and your hands are tired from unrolling scroll after scroll. Most of them are administrative records, tax documents, things that mattered once but feel distant now. Then you reach for another rolled parchment. This one is different. You can feel it. The material is gazelle skin, carefully preserved, and as you unroll it, colour blooms across the table. Blues and greens and golds, coastlines and compass roses, islands scattered like seeds across an ocean. It's a map. A beautiful, intricate map dated 1513. The cartographer's name is written in elegant script. Piri Reis, a Turkish admiral. And as you study it closer, as your eyes trace the shores of Africa and South America, you notice something that makes your breath catch. There, at the bottom of the map, is a coastline, a detailed, carefully drawn coastline of a place that, according to every history book you've ever read, wasn't discovered until 1820, Antarctica. But here's what made scholars stop breathing for a moment. This coastline doesn't just show Antarctica. It shows details that match the actual coastline hidden beneath miles of ice. Details that wouldn't be confirmed until the 1950s, when seismic surveys finally mapped what lay under all that frozen water. How could a map from 1513 show something that no one would verify for 400 years? Now, you're probably sitting somewhere comfortable right now. Maybe you're looking at your phone, at GPS coordinates accurate to within a few feet. You can pull up satellite images of any place on Earth. You can trace routes, measure distances, see the world from space. All of this would seem like pure magic to people just a few generations back. But here's the thing. Those ancient map makers, working without satellites or computers, or even decent compasses, sometimes they created maps that show details they shouldn't have been able to know. Details that seem, well, impossible. If you're intrigued by this mystery, if you want to know how the ancients really saw their world, maybe hit that subscribe button. Drop a comment telling me where you are right now and what time it is. I love seeing Tokyo at midnight, London at dawn, Los Angeles winding down, all of us connected by curiosity about the past. Anyway, back to these impossible maps. The Piri Reis map wasn't alone. Over the centuries, scholars have found dozens of ancient and medieval maps that show things they seemingly shouldn't show. Coastlines drawn with strange accuracy, islands in the right places, mountains where mountains actually stand, and every time one surfaces, the same question echoes through libraries and universities. What did the ancients actually know? And more importantly, how did they know it? To understand that, we need to go back, way back, to the very beginning of map-making itself. Back to when the first humans looked at their world and thought, I need to draw this down. I need to remember. I need to share what I've seen. Because the story of maps isn't really about paper and ink. It's about the most fundamental human drive, the need to know where we are, where we've been, and what lies just beyond the horizon we can see. Let's start with the very first maps, the ones made when writing itself was still new, and the idea of capturing the world on something you could hold in your hands was revolutionary. Close your eyes and imagine you're in ancient Babylon, around 600 years before the Common Era. The Euphrates River flows through the city, and you can hear the sounds of the market, merchants calling out prices, animals being led to slaughter, children running through narrow streets. But you're not in the market. You're in a workshop watching a scribe work. In front of him is a lump of wet clay, soft and pliable. He's got a stylus in his hand, just to sharpen and read, and he's pressing marks into that clay with careful, deliberate movements. He's making a map. The oldest world map we've ever found. The Babylonians called it the Imago Mundi, and it's beautiful in its simplicity. At the centre he draws Babylon itself, represented as a rectangle. Around it he marks other cities, other kingdoms. The whole thing is surrounded by a circular ocean, and beyond that ocean, triangular regions he labels as distant, mysterious places no Babylonian has ever seen. This isn't meant to be perfectly accurate in the way we think of accuracy. It's showing relationships, showing what matters to Babylon, showing the known world with Babylon naturally, right at its heart. But here's what's extraordinary about this moment. This scribe isn't inventing the idea of map-making. He's participating in a tradition that's already ancient by his time. Humans have been making maps for as long as we've had property, trade and taxes. Actually, let's focus on those three things, because they're the real reason maps exist at all. Picture yourself standing on the banks of the Nile River in ancient Egypt, maybe around 2,500 years before the Common Era. It's late summer, and the river is starting to recede after the annual flood. For months, the Nile has spread across the valley, depositing rich, dark silt across the fields. This flooding is what makes Egypt possible. It's why this narrow strip of green can support cities and temples and pyramids. But it creates a problem. When the water covers everything, it erases all the boundary markers. The stone that marked where your field ended and your neighbour's began, it's somewhere under the mud now. The irrigation channel that defined property lines, it's been scoured into a new shape. So when the water finally retreats, how do you know what land belongs to whom? The Egyptians solved this with mathematics and surveying. They developed a whole class of professionals called rope stretchers. You can see them in your mind, teams of men walking across the drying fields, carrying long ropes with knots tied at precise intervals. These ropes were their measuring tools. They'd stretch a rope between 2 points, count the knots, record the distance. They'd create right angles using ropes knotted in ratios of 3, 4 and 5. They understood, thousands of years before Pythagoras got credit for it, that certain proportions always created perfect squares and triangles. These rope stretchers were doing more than just resolving property disputes. They were creating the foundation of geometry. The word itself comes from Greek, geo meaning earth, metron meaning measurement, the measurement of earth. And they were making maps. Not maps of the whole world, but precise surveys of fields and estates, drawn on papyrus, stored in temples and administrative centres. These maps were about power and money. If you owned land, you paid taxes, and the government needed to know exactly how much land you owned, exactly how much grain it should produce, exactly how much you owed. Maps weren't romantic or exploratory at first. They were bureaucratic. They were about control. The Rain Papyrus, one of our best sources for Egyptian mathematics, includes problems about calculating field areas, dividing land, redistributing property after floods. Every calculation is geometric. Every solution requires thinking spatially, visualizing the land from above, seeing it as shapes and numbers and relationships. This is map making, even if it doesn't look like the maps you're used to. Now, shift your perspective to the Mediterranean coast. You're Phoenician now, standing on the deck of a wooden ship sometime around 600 years before the Common Era. The Phoenicians were the greatest sailors of the ancient world, and they had a secret weapon. Not better ships, though their ships were excellent. Not better navigation tools, though they were skilled with the stars. Their secret weapon was information. Every time a Phoenician ship left port, it was gathering data. The captain noted landmarks, how many days of sailing from here to there, what the coastline looked like, where fresh water could be found, where rocks hid just below the surface, where currents ran strong. This information was valuable, more valuable than the cargo in the hold. Because if you knew the safest, fastest routes, you could trade more efficiently than your competitors, and the Phoenicians compiled this information. They shared it within their network of city-states. They created mental maps, and probably physical maps too, though almost none have survived. We know they circumnavigated Africa, probably under contract to Egyptian pharaoh, Necho II, around 600 years before the Common Era. The Greek historian Herodotus tells us about this journey, and he includes a detail that he found unbelievable, but that actually proves the story true. The Phoenician sailors reported that as they sailed south around Africa and then turned north, the sun was on their right side at midday. Herodotus thought this was ridiculous. But we know now that this is exactly what happens when you cross the equator. The sun appears in the northern part of the sky instead of the southern. The Phoenicians saw this, they reported it, and they mapped it. But here's where understanding gets fuzzy. Most Phoenician records are lost. Their cities were destroyed, their libraries burned, their knowledge scattered. We know they had maps because later sources reference them. We know they had extraordinary geographical knowledge because their trading posts stretched from Spain to the Persian Gulf. But we can't examine their actual maps. We can't see how they represented the world. This is important to remember as we talk about ancient cartography. So much has been lost. When you see an ancient map that shows surprising accuracy, part of the mystery is just the mystery of survival. We're seeing the few documents that happened to endure fire, flood, warfare, and simple decay. For every map that survived, Hundreds or thousands probably didn't. Think about what a map meant in this era before paper, before printing, before any kind of mass production. A map was a unique object. If it was on clay, it was heavy and fragile. If it was on papyrus or parchment, it was expensive and delicate. Making a copy meant redrawing everything by hand, and each copy introduced new errors or changes. Maps were rare enough that most people would never see one in their entire lives. The knowledge they contained was literally concentrated in a handful of places: libraries, palace archives, temple collections. Lose one library, and you lose centuries of accumulated knowledge. This happened repeatedly throughout history. And it helps explain why some ancient maps are surprisingly good, while others from later periods are surprisingly crude. Knowledge didn't progress in a straight line. It accumulated, it scattered, it got lost, it got rediscovered. The Babylonians and Egyptians and Phoenicians were solving practical problems: how to divide land fairly, how to navigate trade routes profitably, how to collect taxes efficiently. But they were also asking bigger questions. What shape is the world? How big is it? What lies beyond the places we know? And here's something most people don't realize. They figured out pretty early that the world wasn't flat. You're standing on a beach, let's say, in ancient Greece now, around 500 years before the Common Era. You're watching a ship approach from the horizon. First you see the top of the mast. Then gradually, as the ship gets closer, you see the sail. Then the hull. The ship isn't rising out of the water. It's coming over a curve. The ancient Greeks noticed this. They also noticed that during lunar eclipses, the Earth's shadow on the moon was always round. No matter what angle the Earth was at, the shadow was circular. The only shape that always casts a round shadow is a sphere. They noticed that as you travelled north or south, different stars appeared in the sky. The North Star sat higher in the sky the further north you went. This made sense if you were moving across the surface of a sphere, tilting your perspective. It made no sense on a flat surface. So by around 500 years before the Common Era, educated people in the Mediterranean knew the Earth was round. The question wasn't flat or sphere. The question was, how big is this sphere? And that question was about to be answered by one of the most elegant experiments in the history of science. What those early map makers were really doing, whether they fully realized it or not, was building a framework for understanding space itself. They were learning that the world could be measured, calculated, described mathematically. That knowledge from different places could be combined to create larger understanding, that the Earth, vast as it seemed to any individual human, was actually knowable, mappable, comprehensible. And this realization, this confidence in human ability to observe and record and understand, would lead to achievements that still seem almost impossible. Measurements so accurate they wouldn't be improved upon for over 1,000 years. Maps so detailed they guided sailors for centuries. Knowledge so precise that modern scholars sometimes struggle to explain how it was acquired. But before we get to those achievements, before we see just how good ancient cartography became, we need to understand the breakthrough that made it all possible. The moment when humans went from drawing rough sketches of their local area to creating true mathematical models of the entire planet. That moment happened in Alexandria, Egypt, with a man, a well, a stick, and the shadows they cast at noon. Now we're going to meet the people who transformed map-making from art into science. The Greeks who looked at the world and said, this can be measured, this can be known, this can be calculated with precision. Picture yourself in Alexandria, Egypt, around 240 years before the Common Era. This is the greatest city in the Mediterranean world. The lighthouse at Pharos, one of the 7 wonders, guides ships into the harbour. The Library of Alexandria, the largest collection of knowledge ever assembled, sprawls across multiple buildings. Scholars from across the known world gather here to study mathematics, astronomy, geography, philosophy. And you're meeting one of them. His name is Eratosthenes, and he's the chief librarian. But today he's not in the library. He's standing in the courtyard at noon, watching a vertical pole cast a shadow. This doesn't sound revolutionary. A stick and a shadow. But what Eratosthenes is about to do with these simple tools will allow him to measure the entire circumference of the Earth, and he'll get it right to within about 2% of the actual value. Here's how it works, and you can follow along step by step because it's beautifully simple. Eratosthenes had heard that in Syene, a city about 5,000 stadia south of Alexandria, something interesting happened at noon on the summer solstice. The sun shone directly down into a deep well, illuminating the water at the bottom with no shadows. This meant the sun was exactly overhead, perfectly vertical, no angle at all. But in Alexandria, on that same day at that same moment, the sun wasn't directly overhead. Eratosthenes measured the angle. He set up a vertical pole, a gnomon, and when the sun reached its highest point at noon, the pole cast a shadow. By measuring the length of that shadow and the height of the pole, Eratosthenes could calculate the angle of the sun's rays. It was about 7 degrees. 7 degrees out of the full 360 degrees of a circle. Now here's the brilliant part. If the Earth is a sphere, and the sun is far enough away that its rays are essentially parallel when they reach Earth, then the angle of the shadow in Alexandria directly corresponds to the curvature of the Earth between Alexandria and Syene. Think of it this way. Imagine two sticks poking out of an orange, both pointing toward the sun. If the orange is small enough and the sun far enough away, the angle between those sticks equals the angle of the curve between them. 7 degrees is about 1/50th of a circle, so the distance from Alexandria to Syene, about 5,000 stadia, must be 1/50th of the Earth's total circumference. Multiply 5,000 by 50, and you get 250,000 stadia. That was Eratosthenes' answer. The Earth's circumference is 250,000 stadia. Now, scholars debate exactly how long a stadion was. Different cities use slightly different measurements, but most estimates put Eratosthenes' calculation at around 40,000 kilometres, maybe 46,000 kilometres. The actual circumference of Earth at the equator is just over 40,000 kilometres. He was astonishingly close. Think about what this means. With just geometry, with observations anyone could make, with measurements using basic tools, a human being in the 3rd century before the Common Era calculated the size of the planet. No satellites, no modern instruments, just a stick, a shadow, and brilliant reasoning. But Eratosthenes didn't stop there. He also tried to map the known world using a grid system. He drew lines running east to west and north to south, creating a framework for locating places. This wasn't quite latitude and longitude as we know it. The lines weren't evenly spaced, and they didn't cover the whole globe. But it was the beginning. It was the recognition that you could create a coordinate system, a mathematical framework for describing where things were. Other Greek scholars built on this foundation. Hipparchus, working about a century after Eratosthenes, refined the grid concept. He proposed dividing the Earth into 360 degrees both horizontally and vertically. He suggested using astronomical observations to determine precise positions. If you observed the exact time of a lunar eclipse from two different locations, you could calculate the longitude difference between them. This was theoretical for Hipparchus. The timing instruments weren't precise enough to make it practical, but he understood the principle. He understood that the heavens could be used to map the Earth. By around 150 years after the Common Era, this Greek geographical knowledge had been compiled and systematized by Claudius Ptolemy, a scholar working in Roman Egypt. Ptolemy's geography was the most comprehensive atlas of the ancient world. It listed about 8,000 places, each with coordinates of latitude and longitude. It included instructions for creating map projections, methods for transforming the curved surface of a sphere onto a flat piece of parchment. Ptolemy understood that any flat map of a round world involves distortion. You can preserve shapes, but not sizes, or sizes but not shapes, but you can't preserve both perfectly. He offered multiple projection methods depending on what the mapmaker wanted to emphasize. Think about this for a moment. Ptolemy was solving the same problems that mapmakers wrestle with today. How do you represent a three-dimensional object in 2 dimensions? How do you balance accuracy in different regions? How do you make a map that's both mathematically rigorous and practically useful? And he was doing this in the 2nd century, without computers, without calculus, without any of the mathematical tools we take for granted. His maps, when they were finally rediscovered and printed in the 15th century, guided European exploration for decades. Columbus probably used Ptolemy's coordinates. Magellan certainly did. These maps, based on 2nd century knowledge, remained the best available information for over 1,000 years in some regions. But here's where it gets really interesting. Ptolemy's information came from centuries of accumulated observations. He cites earlier geographers like Marinus of Tyre. He references travellers and merchants and military commanders. He's compiling reports from people who actually walked or sailed to these places, people who measured distances and noted landmarks and recorded directions. The Greek world was connected to an enormous trade network. Merchants travelled from Spain to India. Caravans crossed the Sahara. Ships sailed the Red Sea and the Persian Gulf, and everywhere they went they gathered information. How many days from this port to that one, what direction to travel, what the land looked like. This information flowed back to centres of learning like Alexandria. Scholars there compiled it, organised it, tried to fit it into mathematical frameworks. They were creating something unprecedented, a data-driven model of the Earth. When positions didn't quite fit, they adjusted. When new information came in, they updated. This was collaborative, iterative, accumulative knowledge building, not one genius having a flash of insight, but generations of observers and thinkers building on each other's work. The Greeks also understood climate zones. They noticed that temperature and weather patterns correlated with latitude. They divided the Earth into climata, bands running east to west with similar conditions. The equatorial zone was thought to be too hot for habitation. The far northern zones too cold. In between were temperate zones where civilizations flourished. This wasn't quite right. They overestimated how hot the tropics would be and how cold the polar regions were. But the basic principle was sound. Climate correlates with distance from the equator, with the angle of the sun's rays. They were thinking globally, understanding that patterns they observed locally would repeat at similar latitudes elsewhere. This let them make predictions. If a place was at the same latitude as Egypt, it probably had similar weather. If a coast ran north to south, it probably experienced similar winds and currents to other north to south coasts. These predictions weren't always accurate, but they were rational. They were based on observation and extrapolation. They were science. What's remarkable is how quickly this knowledge could be applied. A merchant who'd never been to India could consult Ptolemy's coordinates, compare them to familiar places, and get a sense of distances and directions. A military commander planning a campaign could estimate how long it would take to move troops based on the terrain and climate described in geographical texts. A ship captain could plot a course using the stars, knowing that certain star positions corresponded to certain latitudes. This wasn't just abstract knowledge, this was actionable intelligence, and it spread. Greek geographical knowledge influenced Roman understanding. It spread east to Persia and India. It influenced Arabic scholars. For centuries, this framework, this mathematical approach to describing the Earth, was the gold standard. But here's the thing about knowledge. It's fragile. It lives in books and in the minds of people who understand those books. Burn the books, and you lose the knowledge. Lose the scholars who can read and apply the mathematics, and the knowledge becomes meaningless symbols on degraded parchment. And both of those things were about to happen. The Roman Empire, which had preserved Greek learning even if it didn't always advance it, was about to fracture. Libraries would burn, cities would fall, trade networks would collapse, and the sophisticated geographical knowledge that Ptolemy had compiled, that Eratosthenes had calculated, that Hipparchus had refined, it was going to vanish from much of Europe for over 1,000 years. But before we talk about loss, let's appreciate what had been achieved. By the 2nd century of the Common Era, humans had measured the Earth's circumference accurately. They'd created a coordinate system for precisely locating any place on the planet's surface. They'd developed multiple methods for projecting the globe onto flat maps. They'd documented thousands of places with remarkable accuracy, considering the tools available. They'd understood climate zones, ocean currents, seasonal winds. They'd built a framework that treated geography as a mathematical observational science, not just as myth or guesswork. A well-educated person in Alexandria or Rome or Athens could look at a map and understand it. Represented a curved world divided by coordinates, with distances and directions calculated using geometry and astronomy. They could trace trade routes spanning thousands of miles. They could discuss lands they'd never seen with some confidence about conditions there. This was a high point of ancient knowledge, a moment when human understanding of the Earth reached a level that wouldn't be matched again for over a millennium. And what makes the achievements even more impressive is that they were done with such simple tools. No telescopes, no precise clocks, no printing presses to standardize and spread information. Just careful observation, mathematical reasoning, and the patient accumulation of data over generations. Every measurement was made by hand. Every calculation done in the mind or with basic counting tools. Every map drawn individually. The margin for error was enormous, Yet the errors were often surprisingly small. Why? Because the methods were sound, because the mathematics was rigorous, because the scholars understood the principles they were working with. They knew where uncertainty lay. They knew what needed more data. They knew the difference between measurement and speculation. And they built their maps accordingly, distinguishing between well-known regions where coordinates were reliable and distant lands where positions were approximate at best. If you could sit down with Eratosthenes or Ptolemy and show them a modern satellite image of Earth, they would be amazed, certainly, but they wouldn't be confused. They'd recognize what they were seeing, a sphere with land and water, with coordinates and measurements. The tools have changed beyond their imagining, but the fundamental approach, the idea that the world can be known through observation and mathematics, that's the same. They built that foundation. Everything since has been building on their work. But that foundation was about to crack. The world that supported this kind of knowledge, the peaceful trade networks, the wealthy patrons funding scholars, the libraries preserving texts, the schools training new generations in mathematics and astronomy, that world was ending, and when it ended, much of what had been learned would need to be rediscovered, recompiled, rebuilt from fragments. The story of maps over the next 1,000 years isn't really a story of progress. It's a story of preservation, of knowledge surviving in unexpected places, of slow recovery from catastrophic loss. But even in the darkest centuries, even when European maps became simple and symbolic, the knowledge didn't entirely disappear. It moved. It transformed. It waited in other libraries, other languages, other cultures, and eventually it would return to astonish medieval Europeans who had forgotten what their ancestors once knew. The fall of the Roman Empire wasn't a single catastrophic event. It was a long, messy decline that played out differently in different regions over several centuries. But the effects on geographical knowledge were profound and surprisingly swift. Picture yourself in Rome around the year 400. The Western Empire is struggling. Barbarian groups are pushing across the frontiers. Trade routes are dangerous or completely cut off. Cities that once thrived are shrinking. The massive administrative apparatus that governed half of Europe, all of North Africa and the Middle East is crumbling. And with it, the infrastructure that supported scholarly work is disappearing. Libraries still exist, but they're not being replenished with new texts. The copyists who reproduced important works are fewer every year. The scholars who could read Greek, the language in which most geographical knowledge was recorded, they're dying off without training adequate replacements. Latin remains, but Latin geographical texts were often simplified versions of Greek originals. When the Greek texts became unavailable, the Latin summaries were all that remained, and those summaries were sometimes missing the crucial mathematical details that made the Greek work so sophisticated. Here's what's fascinating and a bit heartbreaking. The Romans, for all their engineering genius and administrative competence, never quite matched Greek achievements in theoretical geography. They made excellent practical maps, road maps showing distances between cities, military maps showing terrain and fortifications, city plans of extraordinary detail, but they didn't much advance the mathematical geography that Ptolemy had systematized. They used it, certainly. Roman administrators relied on coordinates and measurements, but they didn't push it further. They didn't refine the measurements of Earth size. They didn't improve map projections. When Roman power collapsed, this meant there wasn't a strong Roman tradition of geographical science to preserve. The knowledge that was lost was mostly Greek knowledge, preserved in Greek texts, understood by Greek-speaking scholars, and as the Greek-speaking eastern parts of the empire separated from the Latin-speaking West, that knowledge became increasingly inaccessible to Western Europeans. By the year 500, you could be a well-educated person in Western Europe and not have access to Ptolemy's geography. You might not know that Eratosthenes had measured the Earth. You might not understand coordinate systems or map projections. The sophistication of second-century geography had simply vanished from your world. But here's where the story gets interesting. The knowledge didn't disappear. It moved. Think of it like water flowing around an obstacle. When one path is blocked, it finds another route. In this case, the knowledge flowed east and south, into the Byzantine Empire, which preserved Greek texts and Greek learning, into Persia, where scholars translated Greek works into Persian and Syriac, and eventually, spectacularly, into the Islamic world. By the 8th century, Arab conquest had created an empire stretching from Spain to Central Asia. The Abbasid Caliphate, with its capital in Baghdad, was wealthy, stable, and intellectually hungry. Caliph al-Mansur and his successors founded the House of Wisdom in Baghdad, a combination library, academy, and translation centre. Scholars there gathered texts from across the known world, Greek manuscripts, Persian texts, Indian mathematical and astronomical works, and they translated everything into Arabic. Ptolemy's geography was translated, Eratosthenes' works were studied. The mathematical and astronomical foundations of cartography were not just preserved but actively studied and built upon. Islamic scholars didn't just copy Greek knowledge, they tested it, refined it, expanded it. They made new astronomical observations, they recalculated the size of the Earth. Al-Mamun, caliph in the 9th century, sponsored a geodetic survey to verify Eratosthenes' measurement. Teams of surveyors went into the desert, measured out a precise north-south distance using carefully calibrated ropes and sighting instruments, observed how star positions changed. Their calculation was remarkably close to Eratosthenes, confirming that the Greek measurement had been essentially correct. Think about this. 1,000 years after Eratosthenes, scholars in Baghdad were replicating his work, not because they doubted it, but because they wanted to verify it with their own observations. That's scientific method. That's building on previous knowledge while maintaining healthy skepticism. That's exactly what had been lost in Western Europe but was thriving in the Islamic world. And then came the mapmakers. Al-Khwarizmi in the 9th century created a revised world map based on Ptolemy, but with corrections from more recent travellers. He recalculated many coordinates, especially in the Islamic lands where he had better information than Ptolemy had possessed. His map showed the Indian Ocean as an open ocean, not landlocked as Ptolemy had thought. This was significant. It meant you could potentially sail around Africa, that the Atlantic and Indian Oceans connected. Ibn Hawqal in the 10th century created detailed regional maps of the Islamic world. These weren't just outlines. They showed roads, cities, mountains, rivers, agricultural regions, climate zones. They were practical tools for merchants and administrators. And they were based on first-hand observation. Ibn Hawqal travelled extensively, gathering information personally rather than relying solely on earlier authorities. But the pinnacle of Islamic medieval cartography came with Muhammad al-Idrisi in the 12th century. Al-Idrisi was born in Morocco, educated in Cordoba, and ended up serving Roger II, the Norman king of Sicily. Roger wanted the best possible map of the world. He gave al-Idrisi resources, time, and access to Sicily's libraries, which contained texts in Arabic, Greek, and Latin. Al-Idrisi spent 15 years on the project. The result, completed in 1154, was extraordinary. The Tabula Rogeriana, Roger's map, showed the known world from the Atlantic to China, from Scandinavia to Central Africa. It was drawn on 70 individual sheets that fit together to form a massive world map. And it was accurate, remarkably accurate for the 12th century. The Mediterranean is recognisable, the proportions are reasonable. The placement of cities and geographical features is often correct within a few degrees. Here's something that surprises people. Al-Idrisi's map is oriented with south at the top. This wasn't an error or a quirk, it was conventional in Islamic cartography. North-up orientation is a later European standard, not a universal requirement. Looking at Al-Idrisi's map today feels disorienting until you mentally flip it. Then you see the Mediterranean stretched out, the boot of Italy pointing down left, the Arabian Peninsula hanging down right. It's the world you recognise, just from a different perspective. Al-Idrisi didn't just create a map. He wrote an extensive geographical text to accompany it, describing regions, climates, peoples, customs, trade goods. This was comprehensive geographical knowledge, compiled from Arabic, Greek and Latin sources, from travellers' accounts, from merchants' reports. It represented the cutting edge of 12th century geography, and almost no one in Western Europe knew it existed. Because here's the strange thing about knowledge moving between cultures. It doesn't always flow smoothly. Translation requires people who know multiple languages and who care about the content. It requires cultural contact and exchange. And medieval Europe and the Islamic world, despite centuries of trade and warfare and proximity, had limited intellectual exchange for a long time. Latin scholars couldn't read Arabic. Arabic scholars had little reason to translate their work into Latin since Latin learning seemed impoverished compared to what was available in Arabic. So Al-Idrisi's map, this masterwork of medieval cartography, remained largely unknown to European mapmakers for centuries. Similarly, while Islamic scholars had preserved and expanded Greek geographical knowledge, most Western Europeans had lost even the awareness that such knowledge existed. The maps being created in medieval European monasteries were very different from what Al-Idrisi was drawing in Sicily. These European maps, often called Teo maps, were symbolic rather than geographical. Imagine a circle representing the world. Inside, a T-shape divides it into three parts. The top of the T is the Mediterranean Sea. The vertical stroke is the Nile, or sometimes the Don River. The horizontal stroke is the Danube. These divisions create three regions: Asia on top, Europe on bottom left, Africa on bottom right. Jerusalem is at the centre, where the T meets. East is at the top, which is why medieval maps often show Paradise, the Garden of Eden, at the very top edge. These maps weren't trying to help you navigate. They were teaching theology and history. They were showing the world as a stage for biblical events, with Jerusalem at its centre, with the known continents descending from Noah's 3 sons. They were beautiful, often richly illustrated with drawings of cities and monsters and biblical scenes. But you couldn't use them to sail anywhere or calculate distances. The scale was wrong. The shapes were wrong. The purposes were entirely different from what Ptolemy or Al-Idrisi had in mind. Now, does this mean medieval Europeans were ignorant or uncurious about actual geography? Not exactly. Practical knowledge continued. Sailors still navigated, merchants still traded, pilgrims still found their way to Jerusalem, but that practical knowledge wasn't being compiled into comprehensive, mathematically rigorous world maps. It was fragmented, local, transmitted orally, or in simple route descriptions rather than sophisticated cartographic documents. Think of it like this. The theoretical framework for understanding geography had been lost in the West. People still knew their local areas intimately. They still travelled successfully. But the big picture, the mathematical model of the Earth as a measurable sphere with calculable coordinates, that had vanished. And without that framework, the detailed observations and measurements that could refine maps weren't happening. Why precisely measure the position of a city if you don't have a coordinate system to place it in? Why calculate distances accurately if your map is primarily symbolic? Meanwhile, in East Asia, a completely independent cartographic tradition was developing. Chinese mapmakers, working from different principles and different knowledge bases, were creating remarkably sophisticated maps. Pei Xiu, working in the 3rd century, established 6 principles of cartography that sound strikingly modern. Use a standard scale, establish a rectangular grid, measure distances accurately, determine correct heights, account for angular measurements, account for curves and detours. These principles, if followed, would produce accurate maps, and Chinese cartographers did follow them, creating detailed maps of the empire with roads, cities, rivers, mountains. These maps served administrative purposes, helping the central government manage distant provinces. But Chinese geographical knowledge faced the same challenge as Greek and Islamic knowledge. It was isolated. Chinese maps rarely incorporated information from beyond the empire's borders. Chinese scholars were aware of regions to the west, certainly. The Silk Road brought trade and some cultural exchange, but comprehensive world maps combining Chinese and Western knowledge wouldn't emerge until much later. The same fragmentation affected other regions. Indian cartographers created maps for specific purposes, often religious, showing pilgrimage sites and sacred geography. Southeast Asian maps existed, but few survived. Sub-Saharan African societies maintained geographical knowledge orally, or in forms that rarely survived into the present. The Viking Age, from roughly 800 to 1100, saw extraordinary maritime achievements. Norse sailors crossed the North Atlantic, settled Iceland and Greenland, reached North America. They navigated using intimate knowledge of sea conditions, star positions, sun angles. They probably used sunstones, calcite crystals that can show the sun's position even through clouds by polarizing light. But they didn't create formal maps in the way Mediterranean cultures did. Their knowledge was experiential, stored in saga descriptions and mental maps, passed from experienced sailors to apprentices. When the Viking expansion ended, much of their navigational knowledge faded. What you're seeing across the medieval world is knowledge existing in pockets, islands of sophistication separated by oceans of ignorance. Baghdad knowing what Rome had forgotten, Cordoba preserving what Paris had lost, Constantinople maintaining what London had never learned, and each tradition operating largely independently, using its own languages, its own conventions, its own authorities. This fragmentation meant that the cutting edge of knowledge in one place might be unknown in another place just a few hundred miles away. It meant that advances in one tradition didn't necessarily benefit others. It meant that when knowledge was lost in one location, it wasn't automatically replaced from elsewhere. But it also meant that knowledge had redundancy. When texts were destroyed in one library, copies might exist in another. When one tradition stagnated, another might advance. The House of Wisdom in Baghdad was destroyed by Mongol invasion in 1258. Tens of thousands of books were thrown into the Tigris, supposedly turning it black with ink. But copies of many texts existed elsewhere, in Cairo, in Cordoba, in Constantinople. The knowledge survived even though that particular collection was lost. Similarly, when Al-Andalus, Islamic Spain, fell to Christian reconquest, many Arabic texts were translated into Latin, finally, making Islamic geographical knowledge available to European scholars. By 1300 or so, the situation in Europe was beginning to change. Contact with the Islamic world through trade, crusades, and conquest in Spain was bringing new knowledge. Greek texts were being rediscovered, either in Arabic translation or in Byzantine libraries. Scholars were beginning to question the simple symbolic maps and ask for more practical, accurate cartography. And here's where things get mysterious and interesting. Because starting around 1300, suddenly appearing in Italian maritime cities were maps of astonishing accuracy. Portolan charts, they were called. Charts for ports. These maps showed the Mediterranean, the Black Sea, and sometimes the Atlantic coast of Europe and Africa with remarkable precision. The coastlines were accurate enough that modern scholars can overlay them on satellite images and see strong correlation. The distances between ports were correct. The compass directions were reliable. Sailors could actually use these maps to navigate, and they did for centuries. But here's the puzzle. We don't know where Portolan charts came from. The earliest surviving examples appear fully formed, already sophisticated, showing knowledge that should have required extensive surveying and mathematical compilation. There's no clear progression from simple to complex. They just appear, beautiful and functional and mysterious. Some scholars think they're based on accumulated sailing directions, compiled over centuries by Mediterranean sailors and finally drawn into map form. Others think they might have roots in lost Roman or Greek maps. Others suggest they incorporated Islamic cartographic knowledge. The truth is, we don't know. The Portolan charts are an enigma, a reminder that medieval knowledge was more complex and sophisticated than the symbolic TO maps suggest. Practical knowledge, the kind sailors and merchants needed, never entirely disappeared. It just wasn't always written down or preserved in the texts that historians study. And sometimes when it was written down, it produced results that still surprise us today. So by 1400, as we stand on the edge of what Europeans would call the Age of Exploration, the state of geographical knowledge was fragmented but rich. Islamic scholars had preserved and extended Greek learning. Chinese cartographers had developed independent, sophisticated techniques. European sailors had practical charts that worked even if they didn't understand the theory behind them. And in libraries scattered across the continents, in monasteries and madrasas and imperial archives, were texts containing knowledge about the world that most people had no access to. The stage was set for a reunion of these scattered knowledge traditions, for the rediscovery of Ptolemy in the West, for the compilation of old and new information into maps that would guide ships to new continents, and for the creation of some maps that would puzzle historians for centuries, maps that seemed to show things their creators shouldn't have known, maps with impossible details. Or as we'll see, details that were only impossible if you didn't understand the long, complex, fragmented history of how humans learned to map their world. Now we come to the heart of the mystery, the maps that launched 1,000 theories and captured imaginations for generations. The maps that seem to show things they shouldn't show, that appear to contain knowledge from impossible sources. Picture yourself back in that archive in Istanbul, 1929, looking at the Piri Reis map. You've gotten over the initial shock of seeing Antarctica on a 16th century map. Now you're reading the notes that Piri Reis himself wrote on the parchment. And here's what makes your heart beat faster. Piri Reis explicitly states that he compiled his map from about 20 source maps. Some were contemporary, from Portuguese and Spanish explorers, but others he claims were ancient. One source, he notes, dated from the time of Alexander the Great. Another allegedly came from a sailor who had sailed with Columbus. Piri Reis wasn't claiming supernatural knowledge. He was claiming access to old maps that contained information from earlier eras. This is important. When people talk about impossible ancient maps, they sometimes frame it as mystery or conspiracy. But the mapmakers themselves often explained exactly what they were doing. They were compiling, they were copying, they were combining old sources with new observations. The mystery isn't that they had secret knowledge. The mystery is whether their ancient sources really existed, and if so, how accurate those sources were. Let's look at what the Piri Reis map actually shows. The Atlantic coast of Europe and Africa, drawn with reasonable accuracy. The coast of South America, particularly Brazil, shown in some detail. This makes sense. Portuguese explorers had been mapping these coasts for decades by 1513. Piri Reis had access to Portuguese charts, probably captured from Portuguese ships. But then, at the southern edge of the map, there's that coastline. Mountains, bays, rivers flowing to the sea. No ice, no indication that this is a frozen wasteland. Just land, drawn as if it were habitable. For centuries, people assumed this was just map-makers' fancy, filling in empty space with imagined geography. But in the 1930s and 40s, as Antarctic exploration advanced, something strange emerged. That coastline, if you rotated and adjusted it, looked similar to the actual coastline of a part of Antarctica called Queen Maud Land, and not the ice-covered coast that explorers saw. The bedrock coast, the land underneath the ice, the shape that wasn't confirmed until seismic surveys in the 1950s. This sparked decades of speculation. How could a 1513 map show Antarctic bedrock? The continent wasn't officially sighted until 1820. It wasn't extensively mapped until the 20th century. The ice covering the land is thousands of years old. The only way to see the bedrock coast is with modern surveying equipment. The theories got wild. Ancient advanced civilizations with sophisticated technology, lost cultures that mapped the world before the Ice Age, Atlantis, aliens, time travelers, every fringe theory imaginable attached itself to the Piri Reis map. But before we dive into speculation, let's look at other supposedly impossible maps. In 1531, Orontius Phineus created a world map that showed Antarctica as a separate continent, centered at the South Pole, with mountain ranges and rivers. This is decades before any European had supposedly seen Antarctica. The continent is too large, and the shape isn't quite right, but it's there, separate from South America and Australia, positioned roughly correctly. How? In 1569, Gerardus Mercator published his famous world map using the projection that still bears his name. Mercator's projection revolutionized navigation because it showed compass lines as straight, making it easy to plot courses, but his map also showed a large southern continent, Terra Australis, occupying the South Polar region. He didn't claim to have evidence for this. He was following a theory dating back to Aristotle, that the Earth needed a large southern landmass to balance the northern continents. But the fact that he put a continent there, roughly where Antarctica actually sits, seems prescient. Then there are the Portolan charts we mentioned earlier. These Mediterranean maps from 1300 onward show coastlines with accuracy that seems to require systematic surveying. Some show the British Isles, Scandinavia, even the Baltic Sea with recognisable shapes. How did 13th century Italian mapmakers accurately depict the coast of Norway? They weren't sailing there regularly. They didn't have the surveying equipment that would emerge later. Yet there the coastlines are, detailed and largely correct. And there's the Zeno map, published in 1558, but claiming to show a voyage from the 1400. It depicts islands in the North Atlantic, some real, some imaginary, and includes a large island called Frisland that doesn't exist. But it also shows parts of Greenland and possibly North America with suggestive accuracy. Was it based on Norse knowledge from the Viking era? Was it partially fabricated? Scholars still debate. What you're seeing across these examples is a pattern. Maps from the 15th and 16th centuries showing geographical features that their creators supposedly couldn't have known. Sometimes the features are real, like Antarctica. Sometimes they're theoretical, like Terra Australis. Sometimes they're based on garbled reports, like Frisland. And sometimes they're accurate in ways that seem to require information from earlier unknown sources. This is where things get tricky, because there are several possibilities, and they're not mutually exclusive. First possibility, the mapmakers had access to earlier maps that we've lost. We know this happened. Ancient and medieval maps were rare, valuable and fragile. Most haven't survived. The ones we have are a tiny fraction of what existed. It's entirely plausible that a 16th century Ottoman admiral had access to Phoenician or Greek or Roman maps that subsequently vanished. Second possibility, the mapmakers were compiling reports from explorers and sailors whose records haven't survived. We know European, African, and Asian sailors were travelling far beyond the routes documented in surviving texts. If a Portuguese ship reached Antarctica in 1500 and never made it home, we'd have no record. But rumours, sketches, verbal descriptions might have reached mapmakers. Third possibility, the mapmakers were extrapolating and guessing, and sometimes they guessed right. If you know South America exists and you're drawing the Southern Ocean, you might sketch in a southern continent just to balance the composition. If you happen to put it roughly where Antarctica is, that's luck, not secret knowledge. Fourth possibility, we're misinterpreting the maps. Projections distort. Copying introduces errors. A coastline that looks like Antarctica might actually be depicting southern South America or a speculative landmass. The mountains and rivers might be artistic flourishes, standard symbols that mapmakers added to indicate land rather than specific geographical features. And fifth possibility, some combination of all the above. Real information mixed with speculation, mixed with copying errors, mixed with lucky guesses. This is probably closest to the truth. Because here's what we know for certain. Maps in this era were compiled from multiple sources. A mapmaker in Venice might combine Portuguese charts, Arabic geographical texts, classical descriptions from Ptolemy, reports from travellers, and their own interpolation to fill gaps. Each element had different reliability. The Portuguese charts were excellent for coasts they'd actually surveyed. The Arabic texts preserved ancient knowledge but might be outdated. Ptolemy was mathematically sophisticated but based on 2nd century information. Travellers' reports range from accurate to fantastical. And the mapmaker's interpolation, their artistic filling of blank spaces, could be inspired guesswork or pure invention. You ended up with maps that were accurate in some areas, speculative in others, and wrong in still others. All on the same document. The Piri Reis map is exactly this kind of compilation. The parts showing well-explored coasts are accurate. The parts showing recently explored regions like Brazil are reasonably good, but with some errors. And the southern region, that mysterious coastline, that's where the real questions emerge. Modern analysis of the Piri Reis map has produced some interesting findings. First, the projection is unusual. It's not a standard projection like Mercator or azimuthal. It seems to be a compilation of several different projections, which makes sense if Piri Reis was copying from multiple source maps drawn using different methods. When you account for this mixed projection, some of the distortions resolve. Second, that southern coastline might not be Antarctica at all. Some scholars argue it's actually the coast of South America, extended further south than it actually goes, and rotated due to projection issues. The mountains and rivers could be the Andes and Amazon basin, misplaced and distorted through copying. This is less romantic than ancient Antarctic maps, but it fits the evidence better. Third, even if part of the coastline does resemble Antarctica, that could be coincidental. If you're sketching speculative southern lands based on limited information, you might accidentally create shapes that later turn out to be close to reality. Mapmakers filled unknown areas with educated guesses. Sometimes the guesses were right. The Portolan chart mystery has a more mundane explanation that actually makes the achievement more impressive. These charts were probably created through a process called traverse surveying. Sailors would record compass bearings and estimated distances between ports. Do this enough times, along enough routes, and you can triangulate positions with surprising accuracy. No sophisticated mathematics required, just careful record keeping and lots of data. Over decades or centuries, Mediterranean sailors compiled this information. Someone, probably in Genoa or Venice in the late 1300s, organised all this data into map form. The first Portolan charts were created. They worked so well that sailors immediately adopted them, and the form became standard. We don't have records of the compilation process because it was probably done by practical sailors and merchants, not scholars who wrote treatises. The knowledge was commercial, even secret. Why would you publish the best navigation information when it gave you a competitive advantage? So the Portolan charts aren't mysterious if you understand them as the end product of centuries of accumulated sailing directions, finally organised into cartographic form. What's impressive isn't that they appeared fully formed. It's that Mediterranean sailors had been compiling such accurate information for so long without anyone writing it down in a form that survived. Similarly, the appearance of Antarctica on maps before official discovery isn't that strange when you realise that speculation about southern continents was ancient. Greek geographers theorised about Terra Australis Incognita, the unknown southern land, based on symmetry. They figured the northern hemisphere had lots of land, so the southern hemisphere probably did too. This theory persisted through the Middle Ages and Renaissance. Mapmakers routinely drew large southern continents, not because they had evidence, but because the theory seemed reasonable. That some of these speculative continents roughly correspond to real Antarctica is partially coincidence, and partially the fact that the South Polar region is the logical place to put a southern continent. Where else would it go? Now, does this mean there's no mystery at all? That everything about these maps is completely explained? Not quite. There are still puzzles. Some Portolan charts show details that are hard to explain through simple traverse surveying. Some compass directions seem more accurate than the instruments of the era should allow. Some island positions are correct when they should have been unknown. And the ancient sources that Piri Reis and others claim to use, did those really exist? We have no surviving examples of Phoenician world maps or Greek maps from Alexander's era, but absence of evidence isn't evidence of absence. Given how few ancient documents survived, it's entirely possible that such maps existed and were still available in the 1500s. Here's what's genuinely remarkable about these maps. Not that they show impossible knowledge, but that they show possible knowledge acquired through impressive means. Ancient and medieval people were observing, measuring, recording, compiling, and preserving geographical information across centuries and cultures. Sometimes this information was lost and rediscovered. Sometimes it was passed down through chains of copying that we can't trace. Sometimes practical knowledge existed long before scholarly knowledge caught up. The maps that seem impossible are actually evidence of how sophisticated pre-modern geography was, how extensive trade networks were, how much cultural exchange happened, how much knowledge was transmitted orally or in documents that haven't survived. They're evidence that our ancestors were curious, observant, and methodical, that they explored further and knew more than we sometimes credit them with, and that the history of human knowledge isn't a simple progression from ignorance to understanding, but a complex web of discovery, loss, preservation, and rediscovery across thousands of years and dozens of cultures. But to really understand how these maps were created, how information that seems impossible was actually possible, we need to step back and ask a more fundamental question. How do you make an accurate map without modern technology? What techniques were actually available to ancient and medieval map makers? Because once you understand the methods, once you see how clever and effective they were, the mystery of impossible details starts to dissolve. The real story, it turns out, is even more interesting than the mystery. So let's solve the central puzzle. How did ancient and medieval people create accurate maps without satellites, GPS, or even reliable clocks? The answer is surprisingly elegant and demonstrates just how far human ingenuity can go with simple tools and careful observation. Picture yourself standing on the deck of a ship in the Mediterranean, maybe around the year 1200. You're a sailor, experienced, probably illiterate, but incredibly knowledgeable about the sea. You've sailed this route, Venice to Alexandria, dozens of times, and every time you're gathering information, not writing it down, not yet, but storing it in your mind. The kind of information that will eventually, through people like you, create those mysteriously accurate Portolan charts. First, you're using dead reckoning. This is the most basic form of navigation, and it's remarkably effective if you're careful. Dead reckoning means calculating your position based on direction, speed, and time. Direction you get from your compass. Not a modern compass, but a magnetized needle floating in a bowl of water or oil. It points roughly north, with some variation you've learned to account for. Speed you estimate from experience. How fast does the ship move through the water? You might trail a knotted rope over the side, count how many knots pay out in a certain time. That's where the term knots for nautical speed comes from. Or you might just feel it, the way the ship handles, the sound of water along the hull. After years at sea, you can estimate speed within a fraction of a knot. Time, you measure with a sand glass. 30 seconds, 1 minute, whatever interval you need. It's not precise, but it doesn't need to be if you're just tracking relative time. So you're sailing, you know you're heading southeast, you know you're moving at about 4 knots, you know you've been on this heading for 2 hours. Simple math tells you you've travelled about 8 nautical miles southeast. Mark that mentally or on a crude chart. Change heading, note the new direction, estimate the new speed, track the time, calculate the new distance. Do this continuously, and you can track your position relative to where you started. Now, dead reckoning accumulates errors. If your speed estimate is off, even slightly, the error compounds over time. If the current is pushing you off course and you don't notice, you'll calculate the wrong position. If your compass is reading a few degrees off, you'll drift away from your intended track. But here's the thing, you're not relying on dead reckoning alone. You're constantly checking it against observations. You see a familiar island, you recognize a mountain peak, you notice the color of the water changing, indicating you're nearing shore. You spot birds that only fly within a certain distance of land. Every observation corrects your dead reckoning, brings you back to known reality. Over dozens of voyages, you learn the relationship between your dead reckoning calculations and the actual landmarks. You learn to correct for prevailing currents. You learn seasonal variations in wind and weather. You develop an intuitive feel for navigation that's astonishingly accurate. And you share this knowledge. When you reach port, you talk with other sailors. They sailed a different route and have different knowledge. You compare notes. You refine your mental map. Gradually, a collective understanding emerges. The distance from Venice to Crete is X. The heading from Crete to Alexandria is Y. The current along the North African coast sets eastward at about Z speed. This information, compiled from thousands of voyages by hundreds of sailors over generations, is more accurate than any individual could achieve. It's crowdsourced data before the concept existed. But let's add another layer, astronomical navigation. You're not just using dead reckoning, you're also using the sun and stars. Every day at noon, you note the sun's maximum height in the sky. This tells you your latitude, how far north or south you are. The principle is simple. The further north you go, the lower the sun appears at noon. The further south, the higher. With an instrument to measure the sun's angle above the horizon, you can calculate your latitude. The instrument might be an astrolabe, a sophisticated device with a rotating arm you align with the sun or a star. More likely, for a practical sailor, it's a cross staff or a simpler device. A stick with a sliding crosspiece. You slide the crosspiece until it spans from the horizon to the sun, and the position of the crosspiece on the stick gives you the angle. It's not as accurate as modern instruments, but it works. You can determine latitude to within a degree or two. And here's where it gets clever. You don't need to do complex trigonometry. You just need to know that when you're at Venice, the noon sun is at angle A. When you're at Alexandria, it's at angle B. If you're at sea and the sun is at an angle between A and B, you're between Venice and Alexandria. If it's at angle B, you're at Alexandria's latitude. You might not know the exact degrees in modern terms, but you know the relationship. You know where you are north to south. Longitude, east to west position, is harder. To calculate longitude, you need to know what time it is at a reference point when you observe a celestial event. Before accurate clocks, this was nearly impossible. But sailors didn't need precise longitude. They had latitude sailing. If you want to reach Alexandria, you sail south until you're at Alexandria's latitude, then turn east and sail along that latitude until you reach land. You can't miss it. This is how transatlantic voyages worked. Columbus sailed south to the Canary Islands, then west along the tradewind latitude. He knew that latitude would take him to the Indies or whatever land happened to be at that latitude going west. He didn't know his longitude precisely, but he didn't need to. So between dead reckoning, coastal landmarks, and astronomical latitude, sailors could navigate effectively and build up accurate knowledge of coastlines and distances. But what about the land-based surveying that created maps of interiors? Different techniques, same principles of careful measurement. Imagine you're an Egyptian rope stretcher again, but now it's the Renaissance and you're working for a European monarch who wants his territories mapped. You've got ropes of known length. You've got sighting instruments, basically telescopes without lenses, just tubes that help you sight along a straight line. You've got an understanding of geometry. You start at a known point, a city whose position has been established, maybe through astronomical observation. You sight to a distant landmark, a church steeple or hilltop. You measure the angle to that landmark from your starting point. Then you travel toward it, measuring distance carefully with ropes, or pacing or counting wheel rotations if you've got a cart. When you reach the landmark, you sight back to your starting point and forward to a new landmark. You measure angles and distances. You're creating a network of triangles across the landscape. Triangulation, it's called, and with enough triangles you can map an entire region. Each triangle's angles and sides can be calculated using basic trigonometry. Errors in one triangle don't necessarily propagate to the next if you're careful about your measurements. Over months or years, a team of surveyors can create accurate maps of large territories. This is how France was mapped in the 1700s, how India was surveyed by the British in the 1800s. But the principles were understood much earlier. Roman surveyors used similar techniques. Islamic scholars certainly knew the mathematics. What changed over time was the precision of instruments and the scale of efforts, not the fundamental methods. Now let's talk about compilation, because this is crucial to understanding those seemingly impossible maps. You're a map maker in 1500. You don't travel yourself, you're not measuring anything directly. But you have sources. You have Portolan charts from sailors. You have Ptolemy's coordinates, recently rediscovered and printed. You have Arabic geographical texts with descriptions and distances. You have reports from explorers. You have earlier maps to copy from. Your job is to synthesize all this into a coherent world map. You start with a projection, a method for putting the round Earth onto flat parchment. Maybe you use Ptolemy's methods. Maybe you improvise. You establish a grid of latitude and longitude. Then you start placing things. Ptolemy says this city is at 30 degrees north, 40 degrees east. Put it there. A Portolan chart shows the distance and direction from Venice to Constantinople. Calculate where that puts Constantinople and check if it matches Ptolemy. Close enough? Good. An explorer's report says he sailed west from Spain for 30 days and reached land. How far is 30 days of sailing? Estimate based on typical ship speeds. Put a coastline there. An Arabic text describes the route from Cairo to Mecca with distances and directions. Calculate positions and add them to your map. But here's where it gets complicated. Your sources contradict each other. Ptolemy's coordinates for some cities don't match the Portolan chart distances. The explorer's report seems too far west, or maybe not far enough. The Arabic text uses different distance units than you're familiar with, so you make choices. You weight sources based on how reliable you think they are. You average different estimates, you use your judgment, and you fill gaps. If you've got good information about the northern coast of Africa but nothing about the interior, you sketch in mountains and rivers where you think they should be. You copy from earlier maps, even if you're not sure they're accurate, because something is better than nothing. The result is a map that's accurate where you have good sources, approximate where sources are weak, and speculative where you have no information, all on the same document. This is why some parts of historical maps are remarkably correct while others are wildly wrong. Different parts come from different quality sources, and this is why ancient sources could actually improve a map in some ways. If Piri Reis really had access to a Phoenician map of the African coast, that map might have been based on direct observation from Phoenician voyages. It could be more accurate for certain regions than anything available in 1513. The Phoenicians circumnavigated Africa. If they mapped it, those maps would be valuable even 2,000 years later. Similarly, if Greek or Roman maps survived showing the Mediterranean in detail, they'd be excellent sources. Centuries of trade and travel went into those maps. The information was solid. Medieval mapmakers who dismissed ancient sources as outdated might actually have been discarding better information than they could compile themselves. So the impossible details on Renaissance maps might come from ancient sources that were actually quite good, combined with contemporary information, mixed with speculation, and filtered through the mapmaker's judgment and skill. Not impossible. Complex. Layered. The product of knowledge accumulated across millennia and cultures. And when you understand the techniques available, when you realize how much careful observation and measurement can achieve, when you appreciate how knowledge was shared and compiled and preserved, the mystery transforms. It's not, how did they know the impossible? It's, isn't it amazing how much they knew through possible means? The real story is more impressive than any ancient astronaut theory or lost civilization fantasy. The real story is human beings observing their world carefully, recording what they saw accurately, sharing knowledge across cultures and centuries, and building up a comprehensive understanding of the Earth using nothing but simple tools, mathematical principles, and persistent curiosity. That's the miracle. Not supernatural knowledge, but natural knowledge achieved through entirely human means. But those techniques, impressive as they were, don't exist in isolation. Maps weren't created by individual geniuses working alone. They emerge from networks of knowledge that spanned continents and centuries. To understand how ancient maps could show details that seem impossible, we need to understand how information flowed across the medieval and ancient world. Picture a map, not of geography, but of knowledge. Imagine lines connecting cities where scholars studied, lines connecting ports where sailors exchanged information, lines following trade routes where merchants carried not just goods, but observations, measurements, descriptions of distant places. This network of knowledge is how maps became accurate. It's how information from one part of the world ended up on maps made thousands of miles away. And it's why some maps show details that seem impossible unless you understand just how connected the ancient and medieval world actually was. Let's start with the Silk Road, because this is the most famous knowledge highway of the ancient world. The Silk Road wasn't a single road. It was a network of routes connecting China to the Mediterranean, crossing Central Asia through some of the most inhospitable terrain on the planet. Deserts, mountain ranges, high plateaus where the air is thin and the weather extreme. But for over 1,000 years, caravans travelled these routes, carrying silk and spices and porcelain east to west, carrying gold and glass and wool west to east, and carrying information in all directions. You're a merchant in the year 800, let's say. You're based in Samarkand, a city at the crossroads of the Silk Road. You don't travel the entire route yourself, that would take years. Instead, you trade with merchants who came from China and with merchants who came from Baghdad. The goods pass through many hands from origin to destination. But so does information. The merchant from China tells you about a new route through the mountains that avoids bandits. You tell the merchant heading west. He tells someone in Baghdad. Someone in Baghdad tells a traveller heading to Cairo. The traveller mentions it to a scholar who's writing a geographical treatise. Suddenly, that new mountain pass appears in an Arabic geographical text, noted as a safe route through the Tian Shan Mountains. Information flows like water, finding channels, spreading out, accumulating in pools where scholars collect and organise it. The Silk Road also carried maps themselves. Chinese maps travelled west. Islamic maps travelled east. When they met in cities like Samarkand or Kashgar, mapmakers could compare them, combine them, create more comprehensive views of the world. A Chinese map might show the eastern reaches of Asia in detail but have only vague notions of the West. An Arabic map might be excellent for the Middle East but sketchy about China. Put them together, and you've got a map spanning both. This happened. We know it happened because we can see the results. Mongol world maps from the 1300s show knowledge of both Chinese and Islamic geography. They couldn't have been created without information exchange along the Silk Road. But the Silk Road was just one network. Even more important for European and Islamic cartography was the Indian Ocean Trade Network. This was the world's largest trading system for over a millennium, connecting East Africa, the Arabian Peninsula, India, Southeast Asia, and China. Monsoon winds made it possible. For part of the year, winds blow from southwest to northeast, carrying ships from Africa and Arabia to India. Then the winds reverse, blowing from northeast to southwest, carrying ships back. Predictable, seasonal, reliable. Sailors learned the monsoon patterns thousands of years ago and built vast trading networks on them. You're an Arab merchant in the year 1000, planning a voyage from Oman to India. You're not exploring. You're following routes that have been sailed for centuries. You know exactly when to depart to catch the monsoon winds. You know exactly which ports to stop at for water and supplies. You know the landmarks, the stars to navigate by, the ocean currents. And you know this because generations of sailors before you observed, recorded and passed down this knowledge. Some of it is written. Texts called periplus, which means sailing around, describe routes in detail. The Periplus of the Erythraean Sea, written around the 1st century, describes the entire Indian Ocean trade network, port by port, with distances, trade goods, and political situations. It's a combination of sailing directions, business intelligence, and geographical knowledge. But most knowledge is transmitted orally, from experienced sailors to apprentices. You learn by sailing with someone who knows, you observe, you remember, and eventually you pass it on. Now, here's where it gets interesting for cartography. These trading networks meant that information about distant places was available in centres of learning far from those places. A scholar in Baghdad had never been to China, but he could interview merchants who'd traded there. He could read accounts from travellers. He could examine goods from China and learn about the regions they came from. He could compile all this into geographical knowledge. Al-Masudi, an Arab historian and geographer from the 10th century, travelled extensively but also interviewed sailors and merchants to learn about places he'd never visited. His descriptions of East Africa, India and Southeast Asia were based partly on personal observation, partly on trusted informants. When mapmakers like Al-Idrisi created world maps, they were synthesizing knowledge from this vast network, and the network included local knowledge that was extraordinarily detailed. Every coast had people who lived there, who knew every bay and inlet, every current and tide. When European explorers arrived in new regions, they didn't discover geography, they learned it from locals. Vasco da Gama's voyage to India is a perfect example. Da Gama is credited with discovering the sea route from Europe to India, but when he reached the East African coast, he hired an Arab navigator named Ahmad ibn Majid. Ibn Majid knew the route from Africa to India intimately. He'd sailed it many times. He guided da Gama across the Indian Ocean using knowledge that Arab sailors had possessed for centuries. Da Gama didn't discover the route. He learned it from someone who already knew it, and this pattern repeated everywhere. When Portuguese sailors mapped the African coast, they were often recording knowledge from African pilots and fishermen. When Spanish conquistadors mapped Central America, they used indigenous guides who knew the terrain. When Dutch traders mapped Indonesia, they relied on local knowledge. The maps that resulted often credited European explorers, but the actual geographical knowledge frequently came from people who'd lived in those regions for generations or centuries. This is crucial for understanding those seemingly impossible details on old maps. A map might show a coastline in Africa with surprising accuracy, not because a European surveyed it in detail, but because an African coastal navigator shared centuries of accumulated local knowledge, and that knowledge got incorporated into a Portuguese chart, which was captured by a Turkish admiral, who copied it onto his compilation map. The information might have originated 1,000 miles from where the map was made, and centuries before it was drawn. As long as the information was accurate when first gathered and transmitted reliably through the network, it would remain accurate. Think about the Portolan charts again. These charts showed the Mediterranean with remarkable accuracy. But Mediterranean sailors didn't suddenly develop surveying skills in 1300. They'd been sailing and observing for thousands of years. Phoenicians, Greeks, Romans, Byzantines, Arabs, Italians. Each generation of sailors added to the accumulated knowledge. By the time someone compiled it all into chart form, the information was incredibly refined. Thousands of voyages had corrected errors. Thousands of observations had confirmed distances and bearings. The network had produced better knowledge than any individual could achieve. And the network preserved knowledge even when civilizations fell. When Rome collapsed, Mediterranean trade didn't stop. Byzantine, Arab and Italian merchants kept sailing. When the Islamic Golden Age ended, trade networks persisted. Knowledge didn't disappear. It just moved through different channels, was held by different communities, was recorded in different languages. Then, when conditions allowed, it could be compiled again. This is why some Renaissance maps show information that seems to come from ancient sources. It might actually come from ancient sources, information that survived in the network even when the original maps were lost. A Phoenician sailors' observation about the African coast, transmitted orally through generations of sailors, eventually recorded on a medieval Arabic chart, copied onto a Portuguese map, compiled by Piri Reis. The information is ancient, the map is new, both can be true. The network also explains how knowledge spread faster than you might expect. When Ptolemy's geography was rediscovered in the West around 1400, it spread rapidly. Within decades, it had been translated, printed and distributed across Europe. Scholars in every major city suddenly had access to second-century geographical knowledge. They could incorporate Ptolemy's coordinates into their maps. This wasn't slow diffusion. This was rapid knowledge transfer enabled by printing technology and scholarly networks. Similarly, when European explorers returned from new voyages, their discoveries spread quickly. Columbus reached the Americas in 1492. By 1500, maps showing the new continents were circulating. By 1520, world maps routinely included the Americas. The network was efficient when it had the infrastructure to support it. But let's also acknowledge what the network couldn't do. It couldn't preserve knowledge perfectly. Every transmission introduced potential errors. Oral transmission might distort details. Translation between languages might lose nuance. Copying maps by hand introduced mistakes. Units of measurement varied by region, causing confusion. A distance measured in Roman miles meant something different than the same distance in Arabic miles or Chinese li. So while the network spread information effectively, it also sometimes corrupted it. This is why old maps are a mix of accurate and inaccurate information. The accurate parts come from reliable observations transmitted faithfully through the network. The inaccurate parts come from errors, misunderstandings, or speculation filling gaps where the network had no information. And sometimes the network transmitted myth as readily as fact. Stories of dog-headed men, islands of gold, fountains of youth. These tales spread through the same channels as legitimate geographical information. Mapmakers sometimes couldn't distinguish between real reports and fantasy. You see this on medieval maps, real cities alongside imaginary kingdoms, accurate coastlines decorated with mythical sea monsters. The network was powerful but not perfect. It was human. It reflected both the impressive capabilities and the inevitable limitations of human knowledge transmission. What made the network truly effective wasn't perfection, but redundancy and self-correction. Information came through multiple channels. If one source was wrong, others might correct it. If one tradition was lost, others preserved the knowledge. The network was robust because it was decentralized, distributed across cultures and continents, maintained by thousands of people, each contributing their small piece. This is the hidden story behind ancient maps. Behind every line on the parchment is a network of observers and recorders and transmitters, sailors and merchants and scholars and translators, each one passing knowledge forward, building on what came before, adding what they learned. The maps that seem impossible are only impossible if you imagine them as the work of individuals. See them as products of networks, and they make perfect sense. The details aren't impossible. They're accumulated, refined over centuries, transmitted across cultures, compiled by mapmakers who are synthesizing the collective knowledge of humanity's greatest information network, the network of travelers and traders who crossed the world, observed carefully and shared what they learned. But there's one navigation achievement that stands above all others, one culture that mapped the ocean itself in ways European cartographers never conceived. To really understand the heights of ancient and medieval navigation, to see what humans could achieve with observation and knowledge transmitted across generations, we need to talk about the greatest navigators in human history. Picture yourself on a beach in Hawaii, around the year 800. You're watching the ocean, watching waves rolling in from the deep Pacific. But you're not watching casually. You're reading the ocean. You're seeing patterns in the swells that tell you about islands hundreds of miles away. You're noting how the waves refract and reflect, how different swell patterns intersect, creating signatures unique to specific locations. You're observing clouds on the horizon, their shapes revealing land beyond the visible sea. You're watching birds, knowing that certain species fly specific distances from shore, that their presence or absence tells you how far you are from land. You're doing this because you're Polynesian, and your people navigated and settled the largest ocean on Earth using techniques so sophisticated that European sailors couldn't believe they worked. The Pacific Ocean covers nearly half the Earth's surface. It contains tens of thousands of islands scattered across an area larger than all the land on the planet, and Polynesians settled them. From Easter Island, thousands of miles from any continent, to Hawaii to New Zealand. Deliberate voyages covering thousands of miles of open ocean, finding islands that are tiny specks in an endless sea. This wasn't accidental. This wasn't drifting and hoping for the best. This was navigation of the highest order, based on knowledge so detailed and techniques so refined that they enabled feats European sailors wouldn't match for centuries. Let's understand how it worked, because this is cartography of a completely different kind. You're not making maps on parchment. You're making maps in your mind, maps of star paths and swell patterns, and bird flight ranges and subtle signs in the ocean itself. Start with the stars, Polynesian navigators memorized the rising and setting, positions of hundreds of stars. They knew which stars rose or set at specific points on the horizon. They knew which stars passed directly overhead at different latitudes. They created what's called a star compass, a mental map dividing the horizon into houses, each associated with specific stars at different times of year. If you want to sail to an island that lies in the house of a particular star, you sail toward that star's rising or setting point. As you travel and stars shift position, you adjust. You're using the entire celestial sphere as your navigation tool, but stars are only visible at night and only when skies are clear. During the day, during storms, you need other methods, so you learn to read swells. Ocean swells are long waves generated by distant weather systems. Unlike wind waves, which are short and choppy, swells are regular, deep, rolling. Different swells come from different directions, generated by different storm systems or trade wind belts. At any given time, you might have 3 or 4 different swells intersecting. To an untrained eye, the ocean surface is chaotic. To a trained navigator, it's a map. You feel the different swells, you note their direction, their period, their height. You recognize patterns. You know that a certain combination of swells indicates you're in a specific region. You know that when swells refract around an island, they create a predictable pattern that you can detect from far away. You can find an island you can't see by sensing how swells bend and reflect around it. The Marshall Islanders, closely related to Polynesians, created physical maps of these swell patterns. Stick charts, made from coconut fronds and shells. The sticks represented swell directions. The shells represented islands. The patterns showed how swells interacted in different regions, how they bent around islands, where they converged or diverged. These weren't maps for navigation. You couldn't take them to sea. They were teaching tools, mnemonic devices to help apprentice navigators learn the patterns. You studied the stick chart on land until you understood the pattern it represented. Then you recognized that pattern at sea. This is cartography entirely different from what we've been discussing. Not showing land from above, but showing ocean dynamics from within. Not static geography, but moving, shifting patterns that change with seasons and weather. Yet it worked. It worked so well that Polynesian navigators could sail from Tahiti to Hawaii, a voyage of over 2,000 miles across open ocean, and arrive at an island chain that represents a target less than 1 degree wide in the vast Pacific. How? They used every available clue: stars for general direction and latitude, swells for position and proximity to land, clouds that form over islands, creating a bright spot on their underside from reflected lagoon light, birds whose flight patterns indicate land direction and distance, watercolour changing as depth varies near islands, bioluminescence patterns that might indicate currents or upwelling, wind shifts that occur near land, even floating debris, seaweed, the smell of vegetation carried on the wind. Every observation was data, every sense was engaged, and the knowledge was systematic, not random. Navigators underwent years of training. They learned from masters who'd learned from previous masters, lineages of knowledge stretching back centuries. They memorized star positions, swell patterns, bird behaviors, weather signs. They learned navigation chants, oral texts that encoded this information in poetic form for easier memorization. They practiced on short voyages, then longer ones, building skill gradually under supervision. By the time you were entrusted with navigating a long voyage, you'd internalized so much knowledge that navigation was almost intuitive. You didn't consciously think through every observation. You felt the swells and knew your position. You saw the stars and knew your direction. You noticed the birds and knew land was near. This wasn't primitive or simple. This was expertise developed to an extraordinary degree, and it enabled Polynesian expansion across the Pacific starting around 1,500 years before the Common Era. Island by island, generation by generation, Polynesians settled the Pacific. They reached Hawaii by around 400, Easter Island by around 800, New Zealand by around 1200. These weren't one-way voyages. Evidence suggests regular return trips between island groups, maintaining contact across thousands of miles of ocean. How do we know this? Archaeology shows similar artifacts and genetic markers across widely separated island groups, indicating ongoing contact. Traditional stories describe specific voyages with named navigators, and when European explorers arrived, they found that Polynesians knew about distant islands, could describe their locations, and in some cases had maintained intermittent contact across vast distances. In 1976, a recreation voyage proved the methods worked. The Hokulea, a traditional double-hulled voyaging canoe, sailed from Hawaii to Tahiti using only traditional navigation methods. No instruments, no GPS, no compass. Just a master navigator named Maupiailug from the Caroline Islands, using stars, swells and observations. They succeeded. Over 2,000 miles of open ocean, and they made landfall within miles of their target. Since then, traditional navigation has been revived across the Pacific. New generations of navigators are learning the old methods. Voyages have replicated ancient routes. The techniques work. They've always worked. European sailors who encountered Polynesian navigators were often skeptical. How could people navigate without instruments, without charts? It seemed impossible. But that skepticism reflected European assumptions about what navigation required. Europeans relied on tools, instruments, written charts. Polynesians relied on knowledge, observation, environmental awareness. Different approaches, both effective, but Polynesian methods worked in conditions where European methods failed. In the age of sail, European ships needed clear skies to take celestial observations. Polynesian navigators could work through clouds by reading swells. European ships needed accurate clocks to determine longitude. Polynesians used integrated observations that didn't require knowing absolute longitude. European navigation was precise but fragile. Lose your instruments and you were lost. Polynesian navigation was robust. As long as you had your knowledge and your senses, you could navigate. Now, here's the important part for our story about maps. Polynesian navigation represents geographical knowledge of the highest order, not recorded on parchment, but encoded in oral tradition, in mental maps, in physical senses trained to read the environment. When we talk about impossible details on ancient maps, we're sometimes assuming that knowledge only counts if it's written down, if it's preserved in forms we recognize. But Polynesians navigated the largest ocean on Earth with precision that European sailors wouldn't match until they had chronometers in the 18th century. And Polynesians did it starting thousands of years earlier. Their maps existed, just not in the form we expect. Their cartography was sophisticated, just not drawn on paper. Their geographical knowledge was extensive and accurate, just not written in books. If Polynesian navigators had drawn their knowledge onto parchment in a form Europeans could recognize, those maps would show ocean routes, island positions, swell patterns, all with remarkable accuracy. They would be hailed as impossibly advanced, but the knowledge existed without being drawn. The maps were mental and experiential. Does that make them less real, less impressive? And here's the broader point. How much geographical knowledge existed in forms that didn't survive? How many cultures had sophisticated understanding of their regions but didn't write it down or wrote it in ways that haven't endured? How many navigators crossed oceans? How many travellers mapped continents in their minds, leaving no trace except perhaps a few details copied onto someone else's map centuries later? When we see impossible details on old maps, maybe we're seeing fragments of this lost knowledge. A Polynesian navigator's understanding of Pacific currents, mentioned to a European sailor, sketched onto a chart. An African guide's description of interior regions recorded by an Arab merchant, transmitted to a mapmaker in Cairo. An indigenous American's knowledge of coastlines, shared with a Spanish explorer, incorporated into a nautical chart. The details aren't impossible. They're remnants of knowledge systems we've lost, fragments of sophisticated understanding preserved in unexpected places. This is why the history of cartography is so much richer than just looking at surviving maps. Every map represents not just what's drawn on it, but the vast network of knowledge it drew from, the observations and skills and traditions of countless people who understood their world deeply and shared that understanding. Some of that knowledge got written down, most didn't, but it existed. It shaped the maps that were created. It explains details that otherwise seem impossible. The Polynesians remind us that human capability is often underestimated, that ancient and traditional peoples weren't primitive or less intelligent. They were solving problems with different tools, different methods, but equal ingenuity. They were creating knowledge systems that in some ways surpassed what came later. A Polynesian navigator could do things a European captain with all his instruments couldn't do. An African trader knew routes and regions that no European map showed. An Asian sailor understood monsoons and currents better than any written text conveyed. All this knowledge existed. Some of it made its way onto maps. Most of it disappeared when the cultures that held it were disrupted or destroyed. What we're left with are fragments, hints, impossible details that are only impossible if we forget how much humans knew, how many ways they had of knowing it, and how little of that knowledge survived in forms we can easily access today. But we can honour it, we can recognise it, we can look at those old maps with their mysterious accuracies and see them not as evidence of lost civilizations or ancient astronauts, but as evidence of human brilliance, human observation, human knowledge transmission across generations and cultures. The real story is always more impressive than the mystery, and the real story of navigation and cartography is a story of humans at their best. Curious, observant, analytical, cooperative, building knowledge across time and space, mapping the world not just with instruments but with insight. So now we're ready to solve the mysteries. We've seen what ancient and medieval people could do, we've understood their methods, we've recognized their knowledge networks, we've appreciated achievements like Polynesian navigation that demonstrate the heights of human capability. Now let's return to those impossible maps and see them clearly, without mystery, without confusion, just as impressive human achievements. Picture yourself in a modern laboratory, probably sometime in the 1990s. You're a cartographic historian, and you've got the Piri Reis map in front of you. Not the original, that's in a Turkish museum, but high-resolution photographs and digital scans. You've also got computer software that can analyse projections, overlay historical maps onto modern satellite images, test different interpretations. You're going to solve this puzzle. First question, does the Piri Reis map really show Antarctica? Let's look carefully. The map shows the Atlantic Ocean with Europe and Africa on the right, South America on the left. At the bottom, where South America ends, there's a continuous coastline extending eastward. This coastline has mountains, rivers, even some place names. For decades, people assumed this was just mapmakers' fancy, decorative filling of empty space. But then Charles Hapgood, a professor of history of science, published a book in 1966 called Maps of the Ancient Sea Kings. Hapgood argued that this coastline was Antarctica, as it looked, before being covered in ice. He claimed the map showed impossible knowledge that could only come from an advanced ancient civilization that mapped Antarctica when it was ice-free thousands of years ago. His work inspired decades of speculation and launched 1,000 documentary programs about ancient mysteries. But here's what modern analysis actually shows. The coastline in question doesn't match Antarctica's bedrock coast very well at all. If you try to overlay it onto a map of Antarctica, even accounting for projection differences, the fit is poor. The mountains are in the wrong places, the proportions are off, the rivers don't correspond to actual Antarctic geology. So what is it? Most likely it's the coast of South America extended further south than it actually goes. Remember, Piri Reis was compiling from multiple sources. Some of his sources showed South America accurately down to the latitude they'd explored. Then the coast disappeared into unknown territory. Piri Reis, following common map-making practice, probably extended the coastline speculatively, filling in what might be there based on the assumption that land continued. The mountains and rivers might be copied from descriptions of Patagonia, the southern region of South America, placed on this extended speculative coast. Alternatively, and this is intriguing, some scholars think the coastline might represent early inaccurate reports of the southern tip of South America, Tierra del Fuego and the Drake Passage region. Early explorers rounding South America faced storms, difficult conditions, confusing geography. Their reports might have been garbled, placing coastlines at wrong angles or extending them in wrong directions. When Piri Reis compiled these reports, he did his best to fit them onto his map. The result was a coastline that's sort of right but rotated and distorted through copying and projection errors. Here's the key insight: map projections matter enormously. The Piri Reis map doesn't use a single consistent projection. It's a compilation, and different parts seem to use different projections. This makes sense if Piri Reis was copying from source maps that themselves use different projections. When you copy a map drawn in one projection onto a map using another projection, you introduce distortions. A coastline that runs north-south on the original might appear to run east-west on the copy. Distances get warped, angles change. Modern cartographers, analysing the Piri Reis map, have identified several different projections in different regions. The Mediterranean section seems to use one projection. The South American section seems to use another. The southern section uses yet another, or possibly is just highly distorted from copying. When you account for these projection shifts, much of the supposed mystery disappears. The coastlines fit known geography reasonably well for the early 1500s. The impossible details become copying errors or speculative extrapolations. What about the notes that Piri Reis wrote claiming ancient sources? Here's where we need to be careful. Piri Reis did claim to use about 20 source maps. Some were contemporary Portuguese charts. That's confirmed and makes sense. He also claimed some sources were ancient from the time of Alexander the Great. Does this mean he actually had Greek maps from the 4th century before the Common Era? Probably not. More likely, he had access to maps that claimed to be based on ancient sources, or that had passed through enough copying that they seemed ancient. Medieval and Renaissance cartographers often attributed their sources to ancient authorities to give them credibility. Saying a map was based on Ptolemy or Alexander's geographers made it seem more trustworthy. These claims weren't always literal. They were assertions of authority and lineage. So Piri Reis might have genuinely believed some of his sources were ancient. He might have been told they were ancient by whoever gave them to him, but that doesn't mean they actually dated to Alexander's time. What about the Portolan charts? Remember, these showed the Mediterranean with surprising accuracy starting around 1300. Modern analysis has mostly solved this mystery too. Portolan charts were compiled from traverse surveys, accumulated sailing directions built up over centuries. The method worked like this. Sailors noted the compass bearing from one port to another and estimated or measured the distance. Do this for hundreds of port pairs across the Mediterranean and you can triangulate positions. Get enough measurements and errors start to cancel out. The result is surprisingly accurate charts, especially for coastlines and port positions. Why did they appear suddenly, seemingly fully formed? Probably because the compilation happened over a short period when someone, probably in Genoa or Venice, decided to organise all the accumulated sailing directions into chart form. Once the first chart proved useful, others copied and refined it. The form spread rapidly because it worked so well. There's no mystery, just a project of data compilation that happened to not leave detailed records. And yes, some Portolan charts are accurate enough that they seem to require more sophisticated surveying than traverse methods should allow. How accurate? Within 1 to 2% for many distances and positions in the Mediterranean. That's impressive. But it's achievable with careful measurement repeated many times. If 100 sailors all estimate the distance from Genoa to Barcelona, and you average their estimates, you'll get close to the true distance. Random errors cancel out. Systematic errors can be corrected by comparison with other routes. Over centuries, the accumulated data becomes very good. Modern recreations using medieval methods have produced surprisingly accurate results. The mystery isn't how they did it. The mystery is more that we forgot they could do it. What about Orontius Phineas showing Antarctica in 1531? This is easier to explain. Phineas was following the ancient theory of Terra Australis, the unknown southern land. Aristotle had argued that the Earth needed a large southern continent to balance the northern landmass. This theory persisted for 2,000 years. Medieval and Renaissance mapmakers routinely drew large southern continents, not from evidence but from theoretical necessity. Phineas put his southern continent at the South Pole, because that's where symmetry suggested it should be. The fact that a continent actually exists there is partly coincidence, partly the constrained possibility. If you're going to put a theoretical southern continent anywhere, the South Polar region is the logical choice. Where else would it go? So Phineas guessed right, but it was an educated guess based on ancient theory, not secret knowledge. His continent is too large, wrongly shaped, and includes features that don't match real Antarctica. He got the existence and rough location right. Everything else is speculation and artistic license. This pattern repeats across the supposedly impossible maps. Each one, examined carefully, turns out to be explicable. Compilation from multiple sources with different projections creates distortions that look mysterious until you account for projection. Copying introduces errors that look like impossible details until you trace the likely source. Speculation and theory-driven mapmaking fills gaps, sometimes guessing right by chance or logic. Ancient sources might actually have existed for some regions, carrying genuine old information. But that information was possible ancient knowledge, accumulated through normal observation and navigation, not impossible ancient technology. The Zeno map showing North Atlantic islands is partially based on real Norse exploration from the Viking era, and partially fabricated or misinterpreted. The real parts preserve genuine medieval knowledge. The fabricated parts reflect Renaissance desires to claim ancient discoveries. Mix them together on one map, and you get a confusing blend of fact and fiction. Are there still mysteries? Sure. Some map details remain hard to explain completely. Some source attributions can't be verified. Some accuracies seem luckier than random chance should allow. But these are minor mysteries, gaps in our knowledge about how specific information was transmitted, not evidence of impossible ancient technology or lost civilizations. The principle is clear. Ancient and medieval people were capable of remarkable geographical knowledge. They observed carefully. They measured accurately. They shared information widely. They compiled data systematically. They created maps that reflected the best available knowledge. Sometimes that knowledge was better than we'd expect, not because of supernatural means, but because we underestimate what careful humans can achieve with simple tools and sufficient time. And here's the beautiful irony. The real story is more impressive than the mystery. An ancient civilization with advanced technology mapping Antarctica would be neat, but it would just be technology. Humans using sticks and ropes and patient observation to measure the Earth, create coordinate systems, navigate oceans, and compile comprehensive maps. That's genuinely awe-inspiring. That's showing what human capability looks like when applied with intelligence and persistence. The Piri Reis map doesn't show that ancient astronauts mapped Antarctica. It shows that Ottoman, Portuguese, Italian, and possibly Greek and Arab mapmakers compiled information from dozens of sources over centuries, synthesized it as best they could, and created a map that represented the cutting edge of early 16th century geographical knowledge. That's amazing. That's a testament to human knowledge networks, cultural exchange, and the long accumulation of observational data. Why diminish that achievement by attributing it to imaginary super-civilizations? Similarly, the Portolan charts don't show that Atlantis mapped the Mediterranean. They show that Mediterranean sailors over 1,000 years observed, measured, compiled, and refined their knowledge until it was accurate enough to guide navigation reliably. That's the real miracle. Polynesian navigation doesn't need lost continents to explain it. It's explained by careful observation, systematic knowledge transmission, and expertise developed over thousands of years. That's more impressive than any alternative explanation. When we strip away the mystery, when we see these maps clearly as human achievements using possible means, they become more wonderful, not less. They connect us to our ancestors who are just as intelligent, just as curious, just as capable as we are. They didn't have our tools, but they had time, patience, and networks of cooperation spanning continents. They built knowledge the hard way, observation by observation, voyage by voyage, generation by generation. And sometimes, just sometimes, they achieved results so good that later people, forgetting what was possible, assumed it must have been impossible. But it wasn't. It was human. Entirely, wonderfully, impressively human. And that's the answer to our original question. How do ancient maps show impossible details? They don't. They show possible details achieved through possible means by possible humans doing impressive work. The impossibility was always in our minds, in underestimation of what ancient people could do, in our forgetting of the techniques they used and the knowledge networks they built. Once you remember, once you understand, the mystery dissolves. What remains is something better than mystery: wonder, appreciation, connection to the long human story of trying to understand our world, one careful observation at a time. Now, here we are at the end of our journey through the history of maps, from Babylonian clay tablets to Renaissance compilations. You've travelled with surveyors in ancient Egypt, sailed with Phoenician explorers, calculated with Greek mathematicians, preserved knowledge in Baghdad's libraries, and navigated the Pacific with Polynesian masters. You've seen how knowledge accumulated, scattered, preserved, and reunited across thousands of years. And maybe now, sitting wherever you are right now, you're looking at the world differently. Maybe you're thinking about the GPS on your phone showing your position to within a few meters anywhere on Earth. That blue dot on the screen, that's the latest iteration of a project humans started thousands of years ago. The desire to know where we are, the need to map our world, the drive to understand our place. And here's something beautiful. The GPS system uses the same fundamental principle that Hipparchus proposed over 2,000 years ago: a grid of coordinates covering the Earth, latitude and longitude, allowing any position to be specified precisely. The tools have changed beyond recognition. Satellites instead of stars, atomic clocks instead of water hourglasses, digital signals instead of hand-drawn lines. But the concept, the mathematical framework, that's ancient. Hipparchus would understand it immediately. Eratosthenes would recognize his measurement of Earth's circumference underlying the system. Ptolemy would see his projection methods reflected in how the round Earth is shown on flat screens. The knowledge is continuous. We didn't start over. We built on what they began. Every map you've ever used, every GPS navigation, every geographic search, it's all standing on foundations laid thousands of years ago by people who looked at their world and said, this can be known, this can be measured, this can be shared. They were right. And they did the hardest part. They established the principles, developed the techniques, created the frameworks that we still use. The maps that seem to show impossible details, they were never really impossible. They were always human achievements, networks of knowledge compiled across cultures and centuries, observations refined through repetition, information preserved through dedication. The real impossibility would have been for curious, intelligent humans not to create such maps, not to observe their world carefully and record what they saw, not to share knowledge and build on what others learned. That would be impossible. What happened, what we've traced through this long night, that was inevitable. Humans mapped the world because that's what humans do. We observe, we measure, we understand, we share, and slowly, patiently, over thousands of years, we build comprehensive knowledge. So the next time you see an old map, think about the network behind it. The sailors who measured distances, the merchants who noted landmarks, the scholars who compiled reports, the scribes who copied manuscripts, the translators who moved knowledge between cultures, the teachers who passed down techniques. Every line on that map represents humans cooperating across time and space to understand our world. And that network continues. You're part of it. Every observation you make, every place you visit, every piece of knowledge you share, you're contributing to humanity's ongoing project of mapping reality. The tools change. The fundamental drive remains the same. We want to know where we are. We want to understand what's around us. We want to share that understanding with others. If this journey through the history of maps has sparked your curiosity, if you've learned something or seen the world differently, maybe hit that subscribe button. Leave a comment telling me what surprised you most, or where you are in the world right now. I love seeing how knowledge still travels, how curiosity still connects us across distances. But for now, as you drift towards sleep, take this with you. Those ancient map makers working by candlelight, calculating with simple tools, compiling from scattered sources, they were doing the same work we do today. Trying to understand, trying to know, trying to make sense of the vast, complex, beautiful world we inhabit. They succeeded more than they knew. Their measurements guided sailors for centuries. Their methods still underlie modern cartography. Their curiosity and dedication built the foundations we stand on. And in their success, in their patient accumulation of knowledge, in their willingness to observe carefully and share generously, they left us more than maps. They left us an example, a reminder that humans at their best are curious, cooperative, patient, and persistent. That we can achieve remarkable things with simple tools if we're willing to observe carefully and build on what others learned. That knowledge isn't found in sudden flashes of genius, but accumulated slowly through generations of careful work. The maps don't show impossible details. They show what's possible when humans work together across time, when we honor what came before, when we build on foundations laid by people we'll never meet, but whose work still shapes our understanding. That's the real story. That's the true achievement. Not mystery, but persistence. Not impossibility, but dedication. Not lost civilizations, but found humanity. Sleep well. Dream of distant shores and ancient calculations, of stars and swells and patient observations. Dream of the long human project of understanding our world. And when you wake, you'll still be part of it, still contributing to the endless map that we all draw together, one observation at a time, forever trying to know where we are and what's around us. The eternal human quest. The map we're still drawing. The knowledge we're still building, thousands of years later, still exploring, still mapping, still human.